Okay, so in the last lecture we saw two different types of curve fitting. The first one was interpolation, the second one was regression analysis, and in this experiment we will be talking about regression analysis. So in regression analysis, say you have a set of data like this, where x is the dependent variable, and based on that you have the value. This is the output variable or the target variable y. Okay. And this is the trend of the data that you can see. So from the visualization you can see that y is actually almost increasing. So as x increases, y value also increases to some degree. Okay. Now instead of fit a curve like this way, instead of like this, we want to fit a line. Okay. We want to fit a line through this point. Okay. It can be a linear line, it can also be a curved line. Okay. For now let's just assume we want to fit a linear line through this point. Okay. Say this is one line, so this is one line we are trying to fit. Okay. So for example this is one line, but again there can be multiple lines that can be fit through this point. So say for example this is another line. We can also fit a line like this. We can also fit a line like this. So this is another line. So question is, which one is the most accurate one? Which one actually best fit the data? So we have to establish a basis that okay, this line is the most perfect line to represent the trend of the data. Okay, so to do that we have to use some algorithm, okay, some method. The most appropriate method to actually do that is known as least square regression. Least square regression. So with the help of this method, we'll be able to identify that among all the possible lines, which one is the best one. Okay, so how do you do that? Now one thing before I go there, okay, you can see all of the data is close to these lines, but as you can see this one in particular, this is far away from where it should be. Okay, in this region it should be closer to here, but as you can see it is far away. So normally this kind of scenario happens in normal data that you can get, real world data. So these are called outlier. Okay, outlier. Okay, so there are different methods, okay, to get rid of the outliers, because as you can see normally you can from the data you can see this should not be here, okay, but in real world the data is very messy. So some of the data that are outliers always come in the data. Okay, so you have to take care of the data, you have to remove the outlier or do something about it. So this is not included in your discussion, so for now just assume that this outlier we just remove it for now. Okay, again there are different methods to deal with the outliers, and that is very important when you do this kind of regression analysis, but that is not included, so I am also excluding that. Let's keep it like this way, and put it here. Let's put it here. Okay. Now least square regression. Okay. So here you can see, say for example I have one point x1, say for example this one, say this is x1 and y1, it is this point. Okay, so this is x1 and y1, this is the first point, and see this is a little further, so let's name it x2 and y2. Okay, then you have x3 y3, x2 y2. Okay, then you have the third point, that is x3 y3. Okay, so for each value of x you have a value of y. Okay, so if you continue this way for last value, so let's name it xn, you will have a value yn. So these are all the pairs of data that you have now. Okay, so what you want to do, we want to fit a straight line through this data. Okay. So what is the characteristics of a straight line? You know, that is, if we have equation, that is y is equals to mx plus c. Okay, this is the equation of a straight line. What is the m? M is the slope of the straight line. M is the slope of the straight line, and this is thus the C is the intercept. This is the intercept. Okay, so this portion, for example, for the red line, this is my C. Okay, and it has a slope that is, say for example, M, and it has a slope. You can calculate the slope like this way, the tangent of the theta. Okay, this is a slope. Now for this green line, we will have another C, and you will have another slope. So these are the variable. These are the variable of this line. Okay, these two are the variables. M, that is the slope, and C is the intercept. That represents the particular line. For different lines, you will have different values of M and C. So what we want to do, we want to find a line. That means we want to find a value of M and C that perfectly fits the data, the best fits the data. So how do you do that? Let's go there one by one. Copy this one. Okay, so let's just, I don't need this one. Now we cannot work with so many lines. Let's just work with only one line. So the points are like this. This is a point, this is a point, this is a point, this is a point. Okay, this is a point, this is a point. Okay, say for example, these are the points, all the points that you have, and we want to fit a line. We want to fit a line like this. For example, this was the line. The line may not go through any of the points. Now try to understand. So this is, say for example, the equation of this line is equals to y, that is we are predicting, is equals to, this is y prime, is equals to theta naught plus theta 1 into x. Okay, theta naught plus theta 1 into x. This theta naught is the intercept, this portion is the theta naught. Okay, and the slope is theta 1. Okay, and this is our prediction, and these are the exact value, these are the true value. Okay, so what we do here is that from each of the point, okay, what you do, from each of the point, you calculate, you draw a line like this. Okay, a normal line. From each of the point, you draw a normal line that is normal to the y-axis like this. Okay, a normal line like this way. From each of the point, whatever the points you have, how many points you have. Okay, from each point, let's draw a line. Let's draw a line. Okay, so this length, this portion, this length is what we call residuals. This is what we call residuals. Okay. So residuals. So as you saw previously, we have a set of points like this from x1 to xn. We have a corresponding y1 to yn. So for each value, for each pairs of x1, y1, xn to yn, we calculate these residuals. Okay, so what are the value? Let's see. If we take like this, y1 minus y1 prime, what does it mean? Y1 is the exact point, this is the exact point, this is the accurate point, this is your y1, and the point it is actually intercepting the line that you are actually predicting, that is your y1 prime. Again, this one is your y2, and this line at this point, this is your y2 prime. So you can think of it like this. This is the error, the residual. That means this is the error that your predicted line is making. So for first one, this is the error. For second one, that is the error y2 minus y2 prime. If you go on and on, you will find yn minus yn prime. for all the values dot dot dot. For all the value, you calculate the error like this way. Okay, so this is the error. So what we do in least square regression, we square these values, we square the error, we square the residuals, all the residuals, individual residuals, we square it. Okay, we square it, then sum them all together. Okay, from top to bottom we sum them all together. So we can write it like this way: summation of I is equals to 1, that is the first point to nth point. From first point to nth point, what we are calculating? Yi, that is the original value, minus yi prime, that is the predicted value, and their square. Okay, so you can think of it like this way: this is your function, this is your function. So let's name it j. Let's name it j. So this is your least square regression function. You can think of it like this way: this was your original value, and this was the prediction. You are taking the difference between these two and squaring it up. Okay, then you are summing all together for all the points. What is the total error you have? So we are actually calculating the total error. Okay, so let's come here. So if we write the line like this way, so j is equals to summation of yi minus yi prime whole square, where I is equals to 1 to n. Okay. Now think of it like this way. So this one y1 prime, what was the original equation? Y prime was your theta naught plus theta 1x, right? Theta 1x. So this was the equation of your straight line. So if I write it like this way, you can also write it like this way: summation blah blah here yi minus theta 0 plus theta 1x, okay, this whole portion, then square. You have to put here an I here. So this is your I is equals to 1 to n. Okay, so as you can see in this equation, this is fixed. This comes from your data. This xi comes from your data. Only this one, this theta 0 and theta 1, is the variables of this equation. So you can say that this is a function of theta 0 and theta 1. So this equation is a function of theta 0 and theta 1. So what do you have to do? We will try different values of theta 0 and theta 1 to get different lines. This was your curve. So there was the data. The data was like this. What are you going to do? For different values of theta 0 and theta 1, we'll get different lines. Okay, different lines. So we want to find the line that has the minimum j. Okay, you can call it the cost function. You can call it the cost function. Cost. You can call it the cost function. That means these values are fixed. This one is fixed. This one is fixed. You can say iteratively change the values of theta 0 and theta 1, and for each of theta 0 theta 1 pair, you calculate this distance and calculate the ultimate cost. That is the cost, that is your j. You keep doing it for different values of theta 0 and theta 1. You keep doing it until you find the one that has the lowest j, the one that is giving you the lowest cost. That is your best fitted line, the one that is giving you the lowest difference of all this. That means that line is the most fitted line that can actually represent the trend of the data. Okay, so this is the basic idea of the least square regression method. Okay, so I hope you have understood this. In the next lecture, we'll see how we can actually solve this function. Okay, how can you solve this.